Good afternoon, everyone, and welcome to today's SANCOLD YPF webinar. I've given it a few minutes for everyone to join, but it's time to start. So thank you all for making the time to be here. My name is Ashley Kutsia. I'm the chair of the SANCOLD YPF, and it's my pleasure to host you this morning. Today's session takes us international. It's titled Weir Design and Construction in Queensland, Australia, and it promises to be a valuable one, a chance to learn from a different part of the world and to bring those lessons home to our dam and Weir engineering here in South Africa. Just a few housekeeping notes before we begin. Your microphones and cameras have been disabled during the presentation to keep things running smoothly. We'll hold a questions and answer session at the end, but please feel free to type any questions into the chat as they come to you, and we'll address as many as we can during the discussion. Please note that today's webinar is being recorded, and the recording will be shared on our SANCOLD YPF LinkedIn page a few days from now. With that, let's get started. It's a real pleasure to introduce our speaker, Mr. Chris Nielsen, Chief Engineer of the Queensland Department of Local Government, Water and Volunteers in Australia. Chris is the immediate past chair of Engineers Australia's Civil College Board and serves on several technical committees with Engineers Australia, SANCOLD and SANCOLD. His technical experience spans the numerical modeling of rivers, floodplains, and coastal zones, and he has provided technical oversight and assurance for a wide range of water infrastructure projects. Over the past decade, he has helped establish regulatory and industry guidelines for critical infrastructure, including dam, weir, and levee design, giving him a unique perspective on how technical competence and regulation come together to deliver public safety. Today, Chris will share insights from Queensland's newly developed Weir design guidelines, the first of their kind for the state, and the lessons learned from more than 100 weirs built across Queensland since the 1930s. Chris, we're delighted to have you with us. And thank you also for bringing along your specialist advisors, David and Lee, and we look forward to the presentation. The floor is yours.
Thank you. Thank you very much, everyone. I'll just put my screen on now.
Perfect.
Okay, good. So everyone can see that, I hope. Thank you. Yeah, look, firstly, thank you very much to Ashley for inviting us along. It really is quite the privilege for us to be part of the SANCOLD Young Professionals webinar series. It sounds like it's gaining fame internationally now. We'll be going global before we know it. Well, probably is already. Okay, I might just kick off then. So I'm going to be doing a bit of a tag team presentation. I'm going to be starting with a bit of an introduction and just give a bit of a scene setting. I'm then going to pass on to the two experts that I have in the room with me, Lee Rogers and David Murray. We'll then go through a series of presentations relating to the guideline, and then we can stop and have a Q&A at the end. So the picture on the right, that's the office of the Chief Engineer for Water Infrastructure in Queensland. So as you can imagine, we are the real heroes of the government. We are what makes it happen. We are awesome. Very fortunate to have Lee and David working in the department after all these years. They can introduce themselves when they do their presentations, but just pretty succinctly, public service in Queensland has been progressively reducing the number of engineers that are present operating within the department and within the government. And this has been happening since the 80s and the 90s. We're now in a position where most of the work that is done by consultants. And there's nothing particularly wrong with that, but what we do find is that when it comes to making some of the bigger decisions, sometimes the knowledge base and the background and the context to making those decisions is not there. So we're very, very lucky to have David and Lee, and I really just they make me look good, which is great. I might leave it to Lee to talk a bit more about the Weir basis for the Weir guideline. But I might just quickly touch on a couple of slides to explain the difference. And this is something which I didn't really pick up on myself until we started doing this exercise. What is the difference between a weir and a dam? So a weir is a barrier across a watercourse intended to raise water levels on the upstream side for storage. So that sounds like a dam as much as a weir. It's generally located within the banks of the watercourse. Again, I guess similar to a dam, but differently. During flood events, it can be overtopped. And usually when it is overtopped, and particularly when it's out of bank and severe flooding, you end up with a drowned flow condition at a weir. And that's quite an important distinction, because it means that once you get to some of the big flood events, which are the design constraints for dams, a weir is simply a submerged structure and it doesn't have those same forces. So it means that there's a very different force loading, and there's less safety obligations and less safety concerns as well as a result of that. I've got an example here of two structures that are up in Townsville, up in North Queensland. Ross River Dam, that's the picture in the top right. This dam is, it's got an enormous consequential aspect associated with it. Off to the right there is about another 10 kilometres of embankment. There's houses all the way around. If that dam was to fail, there would be significant loss of life. As a flood gets worse at that particular dam or gets more severe, water levels rise, the force loading on that structure becomes worse, and you need a much, much stronger structure. Now, at the same time as that flood event was occurring there in 2019 with the gates open, further downstream is Applin's Weir. Now, as you can see, that weir is close to becoming drowned. It's at bank full flows, and we're probably at a point where the tailwater condition is starting to result in less force loading on that structure than what it was when the flow was a bit less. So that's probably something to keep in mind. To me, that's an important distinction that we need to keep in mind between a weir and a dam. And that's really where we started from with this work. So I'm going to hand over now to Lee, and he's in a way going to be giving us the origin story for the Weir guidelines. So Lee, can I hand over to you now? Is everything ready?
Well, you can, Chris, thank you. Good morning to everybody in South Africa. Good evening to my colleagues in Queensland. Listen, just very quickly, I'll explain a little bit about my career, which has been rather long. The first 25 years or so I spent all in design and construction. I was involved in quite a few of the large dam projects in Queensland, quite a few of the weirs, some of the long pipelines. But one of the best things that happened during that first 25 years was that I was asked to be Secretary of SANCOLD in the early 1970s, and that was hugely beneficial for me. I met a lot of the practitioners in Australia at the time. Each annual general meeting was actually a study tour in one of the Australian states. So I got to see a lot of projects under construction. And one of the most beneficial things was that most of these projects were actually state government projects. The exchange of information, drawing specifications was absolutely free and very generous. So we weren't reinventing wheels all over the place. It was a good period. So I'm very happy to contribute to this SANCOLD event. Later on, I was the director of design for a period of 3 years in the late 1980s. I moved up to the executive service. That was a more troublesome time because the development program was starting to wind down. There were a number of changes of government, changes of priorities. So by 2001, I thought, I think I've had enough of this and decided to retire. That didn't last very long. I was invited back to provide advice to the Department of State Development in 2002, January, and I've been working, providing advice pretty much continuously ever since. Thankfully on a part-time basis, so I can fit in quite a few other things. Done quite a lot of work with the CSIRO, that's the Commonwealth Scientific and Industrial Research Organisation here, technical review roles with Water New South Wales and Murray Goulburn Water in Victoria. So it's been a very long career, very rewarding career. I hope you young professionals in South Africa might experience a similar rewarding career. So slide 1, thanks, Chris. So this all started with the Weir project, the politician's statement, the largest weir constructed in Australia since World War II. I might be wrong, but I suspect it's the largest weir built anywhere in Australia at any time. It's a pretty challenging project for a couple of reasons that I'll come to soon. But it's in the Fitzroy River catchment. The little red dot on the right-hand bottom picture is the location of the site. So it's well downstream of the catchment. The catchment area above the weir is 140,000 square kilometres. It experiences very big flow events. Mean annual flow recorded 4.76 million megalitres. The maximum recorded flow volume 37.14 million megalitres. And these flood events are typically very long duration in the summer season, typically November to March or thereabouts. So it's quite a big structure. It's spillway crest above bed level, 16.2 metres. The overall length of the structure, 350 metres. And the storage capacity, 74,000 or so megalitres, which is rather more than quite a few of the dams we've built in Queensland. So next slide, thanks, Chris. So the major challenges, there are a lot of them, but I'll only refer to a few. The diversion during construction was obviously going to be a huge issue, given the size of the river, duration of flood events. The site geology was sort of favourable, but unfavourable. There's rock exposed on the right bank and across the riverbed. The left bank, which is the one closest to us on the picture, is all alluvium, 25 metres high. Obviously, the most critical element of this whole structure is that abutment. If it starts to erode, problems. So getting the hydraulic behaviour right was obviously going to be very critical. I'll talk more about that later. And weirs now are far more complex structures than they used to be in the good old days because of all the environmental obligations, the requirements for fish transfer, in this case, turtle transfer for the first time anywhere in Queensland. And there were quite onerous offset obligations. The next slide, thanks, Chris. So how was all this project implemented? Firstly, it was a joint Commonwealth government, state government initiative for funding of $367 million, which was the estimate at the start of the project. The balance of the cost was to be covered by Sunwater, which is the state-owned corporation in Queensland. It was also the development manager and became the ultimate owner of the Weir. The design consultants are GH&D. I'm not sure if they operate in South Africa, but they are a very big company in Australia. The Weir was constructed under an alliance arrangement with Asiana, which is a Spanish-owned enterprise. McCosker Contracting is a regional company in Queensland. Sunwater and GH&D as the its members. So the construction of the Weir took 3 years, and the final cost was $569 million. The major cause of that cost escalation was the fact that the site was inundated 6 times during construction. The construction period was not 2 years, it became 3. There was a COVID shutdown for a month early on in the process. But that's the way of projects these days in Australia, cost overruns. So next one, thanks, Chris. So an important element of the whole Weir design was the technical review panel that was established by Sunwater, comprised 4 engineers and 1 geotechnical engineer, all pretty eminent people. But the unfortunate reality was that only one of those persons had ever been involved in a Weir project before, let alone a Weir project of this size. David Murray and myself, David, the then chief engineer, were termed a client review panel. They had many decades of experience with Weirs, mainly construction, myself, mainly design, as I've told you. We met on all occasions with the technical review panel appointed by Sunwater and the GH&D, the designers, and the Sunwater. It became evident that whilst the design group was pretty eminent in their own specialist fields, hydraulics or geotechnical or structural or whatever, none of them had actually been involved in a Weir before, which is fairly disturbing, there being so few Weirs built in Queensland in recent years. So our involvement was fairly intense. David and myself would have had a great deal to say at very many occasions during this whole process because, as I said, there was a lot of individual technical expertise, but minimal design experience. Later on during construction, Sunwater also established a construction review panel. I didn't have any involvement in that. David might say something about it. So next one. So one thing that we did do during this whole process was to try and raise the awareness of the factors impacting our Weir projects in Queensland for the TRP members. We called it Lessons Learned from Weir Incidents. This is not exactly a new terminology because back in my days of director of design, I remember a book called Lessons Learned from Dam Incidents. It was called the Casa Grande volume. I found it very useful to read that from time to time. It brings one back down to earth, the sorts of things that can go wrong. So what we did was compile data on more than 20 Weirs where there had been total failure or partial failure from 1941 to 2015. By no means an exhaustive list, but we sort of drew from that some primary causes of Weir incidents in Queensland. So next, thanks. So excessive afflux and inadequate protection works are probably the 2 causes of most of the problems that we've had with Weirs in Queensland. The outcome in one case in particular, Marion Weir, if we look at the next slide briefly. Thanks, Chris. Marion Weir is a concrete gravity structure on the left-hand side. It's on the Pioneer River up near Mackay. The left bank was originally where that vertical arrow is. So during a major flood event, that left bank was totally scoured out. The river bypassed the Weir totally. The repair, reinstatement of the storage required the spillway section extending much further over towards the newer left abutment. And I can remember as a young engineer reading a records file on this subject and discovering that repair of this Weir cost twice as much as it cost to build in the first place. So that was not what you might call a very successful project. The picture on the right-hand side is a more modern Weir. It's a step sheet piling Weir in southern Queensland. and you can see the extent of bank erosion there is pretty severe. The protection works here were largely mattresses, but they were not anchored at the top of the bank as they should have been. So the mattresses start sliding down the bank, and you can see the mess that generated there. So back to the previous slide. Thanks, Chris. So flow behaviour during overtopping, a lot of the weirs in Lockyer Valley, which are mostly recharge weirs, suffered bank scar, and these were largely because the cross sections of the weir site weren't symmetrical, or they were near bends. There are very few ideal weir sites in Lockyer Valley, but an awful lot of erosion there. Inadequate condition monitoring. Bedford Weir is an unfortunate example of a rubber inflatable dam installed on top of a concrete gravity weir, where the rubber dam burst unexpectedly on a sunny day. There was a family swimming in the downstream of the weir, and unfortunately a child was drowned. Ungungo Weir was an older structure where a very large hole appeared in the right bank concrete rock fill. Protection works, quite a cave developed under that. The weir was damaged in a flood in 2011, and then again in a subsequent flood in 2013, before anybody actually had inspected the weir and determined that something had to be done to fix it. Design deficiencies, the last picture on that second slide, Chris, Neville Hewitt Weir. A concrete gravity weir with a sheet piling abutment. The entire top lift of this weir fell off during a flood, which was pretty disconcerting. It was more disconcerting because the weir was completed quite some years before that, and the weir had been subjected to bigger floods and longer duration floods than the one during this incident. I happened to be the project designer of this one, so I was very perturbed at the time, and I thought, why did this happen? So it seemed like there were two possible explanations. One was that there was some unusual load condition which we hadn't provided for, and the other one was that perhaps there was deterioration of concrete bond between that top lift and the lifts below. So whichever it was, I'm not too sure at the end of the day, but the rumours in the local hotel were that the locals had been fishing for barramundi using small explosive charges dropped into the weir immediately upstream of the crest. And if that were the case, then there would have been very extreme pressures applied at the upstream face of the weir. So we don't know exactly why, but the top lift has been replaced with passive anchors, and it's still there, thankfully. Okay, next slide. So this is what Weir looked like when it was finished, and I'll just talk through some of the features of this weir, starting on the left bank, which we look downstream when we say left bank. So extending into that field on the far side from the concrete works is a slurry trench cut off of 110 metres or so into the distance. It extends down to rock level and was intended to cut off gravel materials overlying the bedrock, paleo channels. It was something that Dave was very keen to see done, because at Nev Churchill Weir on the Burnett River at Bundaberg, they had attempted to drive steep piling to cut off gravels, and steep piling didn't penetrate through the gravels, and the bank downstream became saturated on filling and whatever. So on that left abutment, you can see that there are 3 step sections. They were developed to allow flow over that abutment earlier than would otherwise occur. And this was very successful in ensuring that we get flow downstream of the weir parallel to the banks. Prior to developing the abutment to that shape, the flow was not very parallel to the banks. There is a large training wall there, and that was again, a very important element in ensuring that we don't get reverse circulating currents adjacent to that bank, which again, as I remind you, is all alluvium, and under no circumstances could we have a failure over there. Downstream of the abutment modulus, there's a short apron, an ant sill, and downstream of that is reinforced concrete slabs and mattresses above that. Downstream of the slabs is riprap. Above that riprap is grassed bank. We had suggested to the consultants that riprap should continue right to the top of the bank, and unfortunately it wasn't, and that is the only area where some scour has occurred immediately above the riprap. So concrete gravity spillway sections under the water, you can see a line, that's the end sill at the end of the apron. The apron is 2 metres below bed level all the way across to ensure that fish coming over the Weir don't land on anything hard, they land in 2 metres of water. So hopefully the number of fish mortalities is pretty low. Over on the right-hand side of the spillway, there are some slotted elevated sections. These were intended to reduce the impact of spillway overflows on fish trying to find the fish lock entrance, which is the fish lock is that large rectangular structure on the edge of the right abutment. There is a 3-level fish lock structure designed to operate over a wide range of headwaters and tailwaters. And on the left-hand side of that structure is the river outlet works. There's a 1.8 metre diameter plunger valve in there that regulates most discharges downstream. And the rest of the right abutment is concrete gravity, and you can see a trough-like structure upstream and downstream of the abutments. That's the Turtle Way. The first Turtle Way put on a Weir in Queensland. I'm not sure that Sunwater would claim that it's been hugely successful yet, but maybe the turtles are still learning how to use it. They climb up each of those slopes, that can rest for a bit, and down the other side, and it's kept perpetually wet by a small pump unit in the outlet works. So that's what the Weir looks like. So far it's performed well. The fish lock apparently is performing very well. There has been a flood that overtopped that fish lock structure, which means there was a great deal of silt to clear out from the structure. But overall, the Weir's doing okay. So next slide, thanks, Chris. I'll only talk about one lesson learned from Rookwood Weir. There are quite a few, but one that I think is the most important one in a way is the issue of hydraulic modelling for a weir like this. Initially, the concept design, GH&D used the CFD modelling to examine flow conditions. I'm not sure that they were very conscious of the fact that it's just so absolutely critical that that left abutment will stand flood overtopping. They plotted the pressure results and the velocities on upstream, downstream sections across the site and concluded that hydraulically the Weir was behaving pretty well. They even concluded that a physical hydraulic model was not needed. This was pretty concerning to David and myself, and we engaged an independent external reviewer to examine what GH&D had done. That review concluded that, yes, well, they'd done CFD modelling competently, but it would be very unusual indeed not to use a physical hydraulic model for such a major structure. So Sunwater commissioned the building of a physical hydraulic model at their laboratories. Next slide, thanks, Chris. Oh, sorry, this one is what the results of CFD modelling sort of typically look like. The left-hand two pictures are a 1 in 2 AEP flood of the final structure, not of the concept design. The right-hand two pictures are a bank full of flood. It's reassuring to note in the top left-hand picture that the higher velocities across the apron and up the end sill get up to the surface and don't attack the bed downstream of the end sill. So it all looks very pretty, but it doesn't actually tell you precisely what's going on. It didn't tell them the very strong reverse circulating currents that were occurring on the left abutment, which I said was the concept design, which didn't have that training wall in it. Useful, but it doesn't show the whole story. So the physical hydraulic model was built. Next slide, thanks. It very clearly demonstrated that we needed to do something about that left abutment, strong recirculating currents, and cross river flow. The solutions that were very quickly developed in the physical model were the left bank training wall and that stepped left abutment. As I said, there are extensive reinforced concrete slabs supported on sheet piling on mattresses downstream. That was essentially because the Fitzroy River carries a great deal of debris, fallen trees and what have you. And it was pretty clear from our experience that the mattresses probably were not going to withstand any impact from large timber debris. So that's what the physical model following arrangement looked like. A scale of 1 in 50 it was. A movable bed was put into the model, even though there was quite a lot of rock exposed. And on the right-hand side, that appears to be a video showing flow over the Weir and over that left abutment. As I said, there are many other lessons learned from the Rookwood Weir project, but I thought I'd just share this one with you as being probably the most significant. So thanks, Chris. That's enough for me.
Thank you, Lee. So I guess this slide might be a little bit premature, but just to wrap that up, once we'd got to that point, we had a couple of documents there that were really valuable, and they were internal. And I guess when we read them, we could see that they were the kind of things which industry really needed to remember, I guess, as much as anything else. And you also could see that there wasn't a lot of other documentation out there that had this kind of advice that Lee's just described. So that was the catalyst to writing the guideline, was to take those two documents and start to think them through and to see what else we could add to that. I'm going to hand over now to Dave. Dave's going to talk through some of the types of weirs that we get in Queensland, and it's pretty much representative of the kind of weirs you get across the globe. So take it away, Lee. Dave, I'll jump to the next slide now.
Thank you, Chris. Well, just a bit of background myself. I graduated over 50 years ago. I had a scholarship with the Irrigation Water Supply Commission, started work with them. We became the Water Resources Commission. Yeah, I first started interacting with Lee in the late 1970s. And for a while, I was stationed out at that physical model laboratory as a design engineer, modelling a lot of weirs and dams for that matter. I then moved into construction, held a very senior role on the construction of the Burdekin Falls Dam, North Queensland, and have been building dams and more from a construction perspective, dams and weirs ever since then. So, as Lee rightly pointed out, he has a lot more design experience, but I probably have a bit more construction experience, which is a good combination. I won't dwell too much on this first slide. I just throw the first one in, a timber crib weir. The timber frames filled with rocks, and I was just trying to reflect. I'm pretty sure I came across one where the locals, this is in the last 10 years, actually tried to burn it down. They weren't that successful, but yeah, there you go. But we really haven't used them since the 50s. Another type of weir is an embankment dam, usually small structures that use concrete slabs to protect against slough. I won't dawdle too much on that because I've never actually had any involvement with an embankment weir, so I really can't add too many more comments to that. Next slide, thanks, Chris. Now, here's what I'd talk about. Lee's taken you through the concrete gravity style weir that Rookwood, and I think Lee's right. In my recollection, it's the largest weir in the country at 16 point something meters. They're very robust. You need solid rock foundations, and you get a dam-like gravity section, vertical upstream face, OG overflow, sloping downstream. But because it's a weir and the tailwater's built up, the structural analysis of this basically means we don't often have to get foundation grouting or anything like that, because the tailwater fills up quick enough to give you counter loads. The other type of weir that's been very common is steel sheet piling, and I've built quite a number of these. You have rows of sheet piling, and then between them you have progressively stepped slabs downstream. They're good for soft alluvial foundations, where current world, the fish environmental concerns now require that the slabs have to be sloping, not stepped. But there's a couple of key things here. When you're building these things in Queensland river systems, you know, you're really exposed to river flows following rainfall events. So you really try to construct these things in the dry season. If you need 2 dry seasons, you construct it to a point where you make safe, then go away and come back the next dry season. But one of the fundamental tricks is we build from downstream to upstream. So on the right of that section, you'll see a row of sheet piling, then there's another row, then there's a concrete slab in between. So what we would do is we'd build those first 2 rows of sheet piling, stop the steel sheet piling, put in the concrete and all the protection works up the bank and downstream. The whole point is, if we were to get hit by an unseasonal flow at that point, there's going to be minimal damage because we've got all our protection works to the height of that second row of piling in place. So you then come and do the next row of sheet piling, and the same thing, you put the concrete slab in, the protection works up the slope, and then you'd come in and do your last row and your upstream impermeable fill. The row of sheet piling to the left is your cut-off, so you typically drive that to some sort of, if you've got some rock somewhere down there or some impermeable fill, but it's your primary cut-off row. But equally well, what we've learned, and it's becoming increasing in recent years, that row of sheet piling to the right, even though it's not that deep necessarily, if perchance you get an unusual scour developing downstream, it's nice to have that row a fair bit deeper as well, because if it starts to backscour, it will prevent it backscouring under your structure. We're dealing with that issue at a Boggabilla Weir. It's on the border with New South Wales and Queensland. They had a scour develop immediately downstream, and Boggabilla Weir is a gated structure, but what they do is use the gates to do releases. And what they really didn't quite fully understand is by just using 1 or 2 gates to do the releases, they're concentrating the flow to a point, and the tailwater level is actually quite low because you're only releasing partial of the full potential, if that makes sense. In that location, that row of sheet piling is 3 meters deep. The scour hole downstream is 2 meters deep. It looks stable, but it's a bit too close for comfort. So we're going to have to do something about that. if that row was more 6 meters deep, we'd be far less worried about it. Sorry, Chris, next one. Minimum energy weirs. The top one is the, that's chinchilla, is it, Lee? Yeah. In the 50s or the 60s, a fellow called Prof. Gordon Mackay at the University of Queensland, who ended up being one of my lecturers, sort of was working and developing this minimum energy loss weirs. Effectively, it's a clever and efficient way, because what you're doing is you're artificially widening, because you can see that weir's in a big arc, so your unit discharge drops off, and it also concentrates the hydraulic jump near the centre line, hence minimising erosion. I think Claremont was the first one built in the 60s, I think, and Chinchilla was built in the 70s, but we don't seem to build these too often. One of the problems Chinchilla had is continued to get damaged following floods, following severe rainfall events, 3 or 4 times, I think. The other type of weir is we have a gated weirs, which is basically more flexibility in operation. But the gates have to be operated appropriately during flood events, like they do on dams. Adds a level of increased level of risk. And barrages, I just mentioned them because we do build a number of barrages in Queensland. They're basically weir type. They can be gated or embankment or the weir type structures to put a barrier between the saltwater and freshwater. You might just go back to that previous slide, Chris. There's something I meant to mention, I forgot. What we see a lot of in is weirs, a combination of the concrete gravity weir and the steel sheet piling. And Rookwood's a good example, but Ned Churchwood that Lee referred to. So in our river systems, they're meandering type things, so it's not uncommon to have good rock on one abutment and across the river, only to be faced with an alluvium on another abutment. And one of the challenges of those alluvium Lee touched on, but I nearly got caught because I was construction manager on Ned Churchwood. With these meandering river systems over hundreds of millions of years, they move around and they leave these channels of dense gravels. Can be up, and if you get anything much over 12, 15 millimeters, you give up on driving steel sheet piling through. So you need another form of cutoff. Now at Rookwood Weir, we knew the geotech had picked up the paleo channels, so we knew the steel sheet piling cutoff wouldn't work, so we got a slurry trench. But at Ned Churchwood, they did a lot of geotech, and it did not pick up any paleo channels, so the designers went ahead and specified steel. When we went to drive the piles, some of them were getting hung up. It turns out there was a paleo channel that went upstream, downstream, that wasn't picked up during the geotech, and we couldn't get the steel sheet piling through it. We tried to grout it. That didn't work real flash. So what happened was, when the water started to build up the full supply level, the downstream left abutment got saturated and was starting to slip in, taking the protection works with it. Fortunately, we were still on site. Contractor was there and he had his batch, and we ended up designing a concrete buttress, so the whole left abutment up until a bit over full supply level is there's a concrete buttress going from the weir downstream to the end of the protection works to stabilise, and that seems to have worked. I guess one of the key lessons there is you're ever working in a you need to be sure, if no matter what your geotech's being saying, if it's saying there's no paleo channels, you need to be sure, because in an alluvial river system, in Queensland particularly, you've got to assume they're there. And you'd need to have good, strong evidence they're not before proceeding. Next slide, Chris. And the next one.
That's it. That's
it. Geez,
that's me.
My bit was quick. My bit was quick and easy.
Thanks, Dave. So I might just spend the next 10 or 15 minutes going through some of the bigger picture side of the guideline and some of the contents that are in it. And we'll start with the critical requirements. So what does a weir need to do? A weir needs to have an ability to store enough water to meet its functional purpose. So, how much water is required, and can the weir provide that amount of water? Number two, can it withstand flood overtopping without significant damage? So once you've known it can hold enough water, will it be able to stay there with flooding? Requirement 3, should not cause harms or negative impacts considered unacceptable to stakeholders. And that captures a range of things. I've written that in the words considered unacceptable to stakeholders. Those stakeholders might be local residents who don't want it there, might want to set fire to it. But it's also regulators, compliance people, and various stakeholders that might consider the environmental impacts to be unacceptable, for example. Requirement 4 is it needs to meet these requirements over its operational life. So it needs to be long-lived. And it has to do all of those within economic constraints. Point 5 is an interesting one because quite often the costs associated with doing a weir project, it starts to touch on, I guess, obligation to communities, obligation to providing irrigation water. So it doesn't necessarily mean it's always would require a positive cost-benefit ratio, but you also just need to be aware that these things may be expensive, even though they do provide a fundamental service to the community. Something that we've had to really have an honest commentary on in the guideline is the decision to stop. Problems tend to appear as the investigations proceed, and if you've spent a year or 6 months doing investigations and then you find a fatal flaw, it can be quite challenging to stop. So you have to be aware of your biases when you're doing that. You don't want to be too optimistic and imagine that your risk won't manifest. And then also have the alternative options on the table and keep an eye out for what other measures there might be. Now, site selection. I kind of like this. So the ideal site is close to the water users, so you don't need much pipe work or channels or anything else to get the water to the users. It's got to have good catchment yield, so it's got to have a really nice big catchment upstream with lots of rain. That rain's got to fall all the time. You can't have a drought, that's no good. You need to have sufficient water storage, but not too much, just enough. Goldilocks water storage. You need to have tolerable environmental impacts, tolerable social impacts. You've got to put it on a place where there's some pretty good geology. If you don't want to have some bank erosion problems, then best to have a nice straight river section, nice stable banks. And then also, if you're going to build this thing out of any particular type of material, you want to have good roads, nice access to quarries. So So yeah, you're talking about a list of things there which you're never really going to be achieving. So you need to think about options. So definitely when you're coming up with a proposal to develop a weir, have a good think about all the different options that might be available to you, different locations, different construction methods, the whole range of different things. Environmental provisions are an enormous challenge to building waterway structures in Queensland. And I'm not sure what that's like in South Africa. But in Australia, in Queensland, there is a really strong emphasis on waterway protection and ensuring that there's not only loss of direct habitat, but also free passage of aquatic fauna as it's travelling through rivers. I've got a huge list of some of the environmental considerations here. It's probably sufficient to say, though, that a lot of the focus is on fish, and it's also on some of the really iconic protected species. We have this famous turtle that happens to breathe out of its butt. It's a very rare turtle living in the Mary River. I think it also has a weed, a green sort of moss thing that it grows on its head like a little mohawk. So we have this green mohawk ass-breathing turtle. Another thing we have is a lungfish. I think there's also lungfish in South Africa, but they're an incredibly unique and rare type of creature. And they're only seen in 6 rivers in southeast Queensland. And then just in general, most of the fish in Queensland and in Australia are generally quite lazy. They're not like the salmon or trout that you might see in other countries leaping out of the water. Generally, we have pretty useless lying around fish that don't really like to be challenged by a structure. So we do have quite a bit of challenge in dealing with environmental approvals. And I don't mean that in a cynical way either. I would also add that, you know, it's critically important that you get these things right. And there is consequential evidence that a lot of the structures that have been built over the years have caused environmental harm. The other one I have there is cultural heritage. That's also a big issue for any kind of construction works in Australia. Investigations are necessary, and they build. So you need to do your investigations in a sequence that is making sense, and you're not wasting time or effort doing investigations until you are sure that you are moving on in the right direction. It includes things like surveys, foundation investigations and geotech, identification of construction materials, having a look at storage impacts and some of the geography aspects, environmental surveys, and stakeholder engagement. I've got a lot on this slide about design, and I probably don't have too much time to go too much into this, and I think that some of the commentary from David and Lee covers quite a bit of it, but probably would say that there's a range of factors that will drive a preferred weir design type and construction methodology. The foundations is one thing that's quite important, but of course, if you don't have access to or availability of materials, then things might change there as well. When you're doing design, you need to consider the demand. How much will people be willing to pay for the water? Will there be enough water to fill the weir? You need to do hydrology. You need to do hydraulic modelling to identify the storage volumes and to understand what happens during flood events. Probably would add that, again, I'm not 100% familiar with the climate in South Africa, but I guess when I have been there, I've seen terrain and geography very similar to Queensland and New South Wales. I probably would say some of the differences, though, is that Queensland is exposed to cyclonic activity. And so we have an extreme variability in our climates because of that. We'll have, in some areas, there will be sustained periods with very little rain, and then a cyclone will come along and we'll have an extraordinary heavy flood event. That creates a lot of challenges for us. Just a few other things there. I'll probably just skim over them pretty quickly. One thing up in that top corner there, we've got this concept of a block weir. This is something which you do need to keep in mind on, that if you build a weir, just be careful that the water won't bypass it. You need to take the outer branches and make sure that they're dealt with as well. We had some specific hydraulic criteria, and these were quite contentious when we started engaging with some of the hydraulic engineering gurus around the place. But they've got a fairly good, solid basis in past experience, and they are very good rules of thumb. And there is hydraulic explanations for them. Happy to share the guideline when we publish it in the next month or so. Bank full is a critical flow condition. So once the water is at bank full, you really don't want the weir to be causing that much afflux at that flow condition. That has a number of reasons, because once the flood goes above bank full, then you're impacting properties. So you're going to be getting that unacceptable flood impact. But then also that afflux is a proxy for the energy that will be imposed upon the banks adjacent to the weirs. And this, quite often in Queensland at least, with the nature of the weir locations, mostly being in particular locations along river systems in the coastal zone of the floodplains, and the types of material we often encounter, that kind of bank afflux threshold is a really good indicator of whether or not there will be bank erosion. Just very quickly touching on construction, I'll focus primarily on the challenge of managing through floods. Quite often we have a requirement, particularly for dams, less so on weirs, but construction during dry season is quite important. And then you need to think about how long will you have if a flood was to come along. So do you have a rain gauge upstream, and then you know if it goes above a certain millimetres per hour, that in 2 days' time a flood will come along and you'll need to clear your site out and get ready. They're the kind of questions that you need to ask, and you need to start running some concepts of risk assessment. You don't want to be caught short, but at the same time, maybe you need to accept a certain risk that you will be. I've spent a lot of time in my previous roles. Before I was the chief engineer, I was the dam safety regulator in Queensland, and a lot of issues associated with poor project delivery come about from the governance and the oversight of those particular projects. Just a couple of things. There's a lot of discussion on some of the aspects that could be considered, but two things I've highlighted there. The weir owner should be an informed decision maker. They should have appropriate technical understanding of the risks. It's a simple thing to say, but it's not that easy to achieve all the time. Operation and maintenance. I probably won't go too much into this. except to highlight this picture on the right. This is one of those examples which you don't really want to hear about. Inflatable weirs were being installed in a few places, on dams and weirs in Queensland and around the world. They were a fairly good idea because they were a fairly quick and easy way to increase upstream storage capacity, and then you could quickly deflate it, and then you could get that subsequent flow release if you needed it. Unfortunately, this one burst and caused I guess a human-caused flood wave downstream, which resulted in the death of a child. Since then, all of those inflatable weirs have been decommissioned. Competencies, probably just to highlight that there's competencies in terms of your skill and what you've learnt at university and the experiences that you have. But then there's the other aspects relating to your behaviour and your competency and the way that you limit what you do based upon what you're competent in. So it's about conduct as much as skills. And a lot of the published guidelines that we have in Queensland relate to those two things. It's not just about the skills, but it's also about how you conduct yourself. We did expand on some of the lessons learned. I probably won't go into that too much. Probably one of the things I might just quickly highlight, though, is two things. The challenges interpreting CFD. Through Engineers Australia, we're in the process of publishing a guideline on the use of CFD, which touches quite a lot on the problem definition associated with doing numerical and physical modelling. And that's about asking if the tool is going to provide the accuracy that you require to make decisions for a particular problem. Not always a straightforward question. The other one is regulatory complexity, and I touch on that because quite often there becomes a engineering delivery versus environmental concern, and it becomes almost like the two don't want to communicate with one another until it gets to a point of a decision, and then it becomes quite a contentious decision. There's a lot of effort required to make sure that a project comes to a conclusion with everybody smiling and everybody happy. So we follow a very rigorous process to make sure that everybody gets a look at the guideline. I apologise that I didn't pass it on to the South African young professionals. That was remiss. But we're now at a point where I'm waiting on the signature of my executive director, my deputy director general. And I'm hopeful that we will have this thing up and published for everyone to have a look in September. And for those of you who feel like making the journey to Australia in October, I'll be doing a presentation at the SANCOLD conference, which is going to be down in Hobart, which is a very lovely part of the world to be in. So with that, I'll end my preso. Apologies for being a few minutes over time. I blame David for talking too much. But I think it's probably better that you had more from those two rather than me. So I'm really happy to hear if anyone's got any questions. Thank you.
Thank you so much, Chris, Lee, and David. We really appreciate the time and effort you put into the presentation. It was very informative, and I think it will spark a few questions. I would like to start the question and answer session. So if you have any questions, please raise your hand. At the moment, I don't see any in the chat. I'm checking the Q&A. Okay, we have one coming into the chat. Okay, I also have a few questions, so we'll start with the one in the chat. Maybe they'll end up asking my question. In my experience, so this is from Russell Payton. In my experience, conventional weir design practice is to limit the afflux at bank full flow, as you have outlined, to less than 0.3 meter to limit flooding impacts and scour. The primary design feature which affects afflux is the crest level of the weir. With developmental approvals associated in building new weirs on greenfield sites, these may be a tendency to raise existing weirs, which inevitably increases afflux, particularly if doing so with a fixed crest. In your experience, would you recommend consultants and weir owners be cautious in relaxing afflux limits at weirs, particularly those sited on alluvium?
I might start to reply to that one, and then I might pass over to Lee. It's a very good question. I mean, you know, we can build a dam very happily to survive more than 0.3 meters of afflux, you know, so it can be done. But weirs are not dams. So we just recommend that there is an excess of caution and additional investigation if you do decide to exceed the 0.3 meter afflux. Lee, do you have anything more to add to that?
Well, I think it could exceed 0.3 afflux in some circumstances, and they might be that you do have rock extending to the top of the bank on both sides. Or it's a weir on a very small catchment where the floods are of very short duration and perhaps infrequent, and you've got opportunity to jump in and repair if need be. But practice over so many decades and so many weirs says 0.3. Don't go beyond 0.3.
Yeah. So I think that's a good rule. And you know, when you think about, you might have a steeper slope where you're putting a weir, but you know, I think there will always be circumstances that are exceptions to the rule, but I think as a general rule for 95% of the time, it's a good one. Yep.
All right, thank you. So, was that the end of the answer?
Yeah,
You
that's
still
it.
have some more.
I was about to jump on to the next question, actually.
Oh, okay. So, yes, you've actually already answered this question in the previous slide, but Johannes Gross is asking, where can we obtain the guidelines?
You know, I really expected that I'd be able to share a link in this presentation. I was really hoping to, but I'm sorry. But it will be soon. It will be soon.
Yeah, so it will be on the website. Maybe when it launches, Chris, you can send me a mail and I can share it on our SANCOLD LinkedIn page. Cool.
Yeah, I'll post it on LinkedIn as well.
Okay, great. We might share it then. Yeah. So couple of the next questions, I think just need some clarity. The presentation was on water supply weirs and not on gauging weirs. But okay, so we've got a question from Adams Naeem, which is asking, in your opinion, will new technology like non-contact radar flow instrumentation ever replace the need of a gauging weir?
Good question. I think if I'm understanding right, that non-contact radar flow, that's the one that is shooting down from above, isn't it? And it's working out the flow distribution across a waterway and providing estimates of discharge. I think that there is some troubles that they have with clearer water compared to cloudier water. And I think that they're not always going to, well, how do I put this? They're not quite as reliable, should we say, as is if you had a water level gauge upstream of a weir. So yes, maybe it will. Will it replace in all instances? I suspect not. Yeah, that's probably my sort of quick answer to that one.
So we have a similar question. So from Rian van der Walt, he's asking, the weirs presented seem to be predominantly associated with water supply infrastructure. Do you also specialize in the design, installation, and monitoring of weirs used for hydrological monitoring and flow measurement?
They're small. These are big. These are much more fun. I in past roles, yes, I have been involved in the monitoring weirs, and the heavy focus on trying to identify the correct rating curves and things like that. So no, I'd probably say that we don't. I'd probably say, so Lee and Dave, I'm just trying to think how many gauging stations we would have that would be weirs. I think that what we've been focusing on is the large river systems, and it's just not realistic that you'd be having a gauging station, specifically with a weir. It'd be for the smaller waterways and the creeks.
There are, Chris, there are a number of the gauging stations that do have very low concrete notch structures, but many of the gauging sites are at rock bars where there is a stable section. I don't know what the percentage with gauging weirs would be, but I suspect it's sort of like 10 or 15% of all the gauging stations in Queensland would have a weir structure.
Very interesting. We have a couple of big gauging weirs that are also exciting to design. But yeah, so I don't see any more questions in the chat or the Q&A, and there's no hands. So I'm going to ask a few from my side. So I can see from some of the pictures that you might also struggle with a high sediment load. There were some rivers that were quite brown there. And I'm asking just how do you manage upstream sedimentation and loading on the weir structure? And do you ever need to remove the deposited sediment? I don't know if you can maybe explain how you go about doing that.
So I'm quite dumbfounded by this, but we don't seem to have as much of a sedimentation problem upstream of structures in Queensland. I'm hearing, for example, Burdekin Falls Dam, that is an enormous dam. That is a phenomenally big dam. And I am hearing that there is some evidence of delta retreat in the Burdekin River. That's about the only time I've heard of a sedimentation impact associated with dams and weirs in Queensland. There's a couple of others. And I was speculating with David this afternoon as to why that is. Maybe it's due to the significant variability in the flow conditions, and maybe the floodplain flow is a large conduit of sedimentation. I'm not sure. Or maybe we just don't monitor it. But whatever it is, we have not got significant operational problems at this stage. Maybe that's the other thing. Maybe it's just a bit slower, and then 10 or 20 years' time we'll be like going, oh, yeah, it was. But right now, no. Dave or Lee, I don't know if you've got any more to add than that.
I'll just add.
What seems to happen on the... You go, Dave.
No, I was about to say, I'm only aware of one weir and it's out west, and I can't remember the name of it now. For some reason, it likes to silt up all the time, but that's the only one. I'm not aware that there's a significant problem. And I know, and Lee, you might remember, there was Jones Weir, was it up north somewhere? They started doing bathymetric surveys every 6 months or so to monitor, and you could see the sediment like a sine curve, just slowly move. It gets up against the wall. Next time they get a flood, it's gone. and maybe it's something to do that the weirs are relatively low height as well. I'm not sure, but it's an interesting comment, that's for sure. Sorry, Lee, your turn.
Typically, what we seem to have is a wedge of sediment on the upstream face of a weir, but only a wedge. You might remember our discussions with CH&D about sort of extreme loading at Rookwood, of assuming that sediment would extend from full supply level horizontally upstream, and we said that just doesn't happen. So as I said, quite a few of the weirs, when they've been become empty for whatever reason, there is a wedge of sediment against the upstream face, but it's only a triangular sort of wedge. And the weir you were talking about that has silted up is Needle Turner Weir on the Maranoa River at Mitchell.
Yeah, that's it, at Mitchell. Yeah, but even that wedge, that study they did on the Jones Weir, that wedge came and went. Part of an ongoing process. So really can't help you much there, Ashley. It hasn't been.
Okay, yeah, no, it's cool. My follow-up question on that is kind of like for the abstraction parts, if you're seeing any issues with the sediment load on your pumps, like do you have hoppers or cyclone separators or filling basins to try and help with the sediment load and the damage on the pipe or on the pump system that you have when you're abstracting? Because that's one major concern for us, and what makes the abstraction weirs quite complicated to design is mostly the sedimentation part. And it's quite interesting that you say you should build your weir on a straight section, where for us on an abstraction weir we would rather opt for a bend, so that you can kind of, you know, choose an abstraction side where the sediment is less favorable to flow toward it. And then for a gauging weir, we would rather have it on a straight section, because obviously we need straight flow lines. And then the sediment is not a concern, because as you said, the weir is self-cleansing in a way. When there's a bigger flood, it goes away. But for abstraction weir, the pump systems are kind of what our concern is. And we have been asked many times if there's anything we can do about it. And I was just wondering how you guys go about solving that problem, if you have the problem.
It's never been one that's actually surfaced as a critical risk issue I had to consider, just to be honest with you. So maybe we're fortunate we have more compliable sediment in Queensland.
Yeah. I think, I again, you know, you've described situations which, you know, I've heard elsewhere. And it did come as a surprise to me that it doesn't seem to be such an issue here. Yeah, figure. There's a study here. Somebody needs to do a study, at least come up with some theories.
It's an interesting question you raise as to why is more of an issue over in your area, and it's not so much an issue for us. That's an interesting question. I'd like to know what the answer is.
Yes, for sure. We have a abstraction weir specialist in South Africa, and most probably he's got some write-ups about this, which I could follow up on, but and maybe share. But yeah, so it would be that that's a specifically, I guess, in Queensland, your sedimentation load is not as high as we have in South Africa, or in some regions in South Africa. So yeah, that's an interesting comparison. So some lessons learned, I guess, could extend the guideline at some point, maybe from a different side. So this is specifically for Queensland's set of experience.
I think so, yeah. I mean, I do make the comment that sedimentation in the guideline, you know, to make the comment that it isn't generally noted as an issue, but you know, nevertheless, it is sort of mentioned there as something that needs to be considered. And that is simply referring to your experience in, you know, most other places. Now, on a similar note, the ICOLD hydraulic committee that I'm on now is looking into the design of low-level dam outlets for the express purpose of sediment transport. And some of the stories and images that you see of structures in Japan in particular, and some of the mountainous countries, it's quite incredible, the sediment load that comes through.
Okay, thank you. I don't see any other hands or questions in the chat, so I'm going to close off the session with just a few advertising slides from SANCOLD. I would just like to thank our speakers for taking the time. It's past 7 there already. They had to stay up late working, and we get to do a morning session. So thank you so much for the sacrifice and for coming to share your knowledge with us. I think we definitely learned a lot, and it's really nice to see that this work is still being done, and that people are still working on improving guidelines and designs and so on. So thank you so much to all the speakers. I see a couple of applause from the audience, and thank you.